Good morning, everybody, and welcome to the Royal Swedish Academy of Engineering Science, IVA. In fact, it's the first engineering academy in the world that was founded in 1919, so we have celebrate 100 years next year, in fact, just some information. Then we have some more seminar on these topics, I'm sure. My name is Johan Karlstedt, and I'm Senior Project Manager of Innovation and Entrepreneurship at IVA. And IVA, as you know, is an independent arena, and we try to influence the development of society and business in different ways, with a mission to promote the engineering and economic sciences and the advancement of business and industry for the benefit of society. Isn't it beautiful? To accomplish that, IVA has a pool of knowledge and experience from 1,300 fellows and 230 businesses that are members at IVA as well. And we offer a transboundary meeting place and an independent arena, like today, that we hold seminar, discussions, and so on. And we also run projects like this one, Smart Industry. And for the moment, Smart Industry focus on digitalization and innovation in small and medium-sized enterprises in Sweden. And we do different things in these projects. For one thing, we do business-to-business forum to have discussions all over Sweden with big companies, small, medium-sized companies, and even startups to help SMEs to take different steps to adapt the possibilities of digitalization. We also host a business competition called Smart Industry. And that is why we want to put forward good examples, best practice, how SMEs use digitalization in different ways and become more competitive. And we also run seminars in these projects and business meetings, like this one, to gather knowledge on digitalization in different matters and areas. So we're very happy today that we have this seminar on additive manufacturing together with Amexi. And I would like to give the floor to the CEO of Amexi, Edvin Resabo. Give him a big hand.
Thank you, Johan. Really nice to see so many people here today. And I want to extend a big hand to Johan and IVA and everyone else who has been involved in planning and setting up this event today. And hopefully we'll all get away from here learning something new. I know I will, at least. So I'm going to talk a little bit about Amexi, who we are, what we do, and then also I've been given the privilege of making a 4-minute introduction to additive manufacturing, so bear with me on that one. Talking a little bit about Amexi then, I mean, we were founded in December last year by an initiative within Investor and the Wallenberg Group to set up a joint venture company where Swedish industries collaborate and accelerate the industrial adoption of additive manufacturing. So we're a solely privately owned entity, and as you can see, we work with an array of industries and in their respective journeys in additive manufacturing. And what is it then that makes additive manufacturing interesting today for the industry? Well, this is an example from Siemens Industrial Turbo Machinery in Finspång, and you will hear Vladimir Nawrotsky from that specific company today talk more in detail of this very nice case. And I think when this technology becomes truly interesting is when we can do things that were not possible before. So what you can see here is an example where I would say all of these nice functions and iterations that has been done and integrated into this product, I mean, one of these bubbles is a business case in itself. But when this technology becomes disruptive is when you find all of these good cases on one single product. It completely changes your business model and how you put something on the market today. And how does it work? I mean, I've been thinking about how complicated pictures we should use for this, but I think in principle, when it comes to additive manufacturing, we start with a CAD geometry of an object, and then we slice that into two-dimensional layers of the same object, and then a machine is told how to recreate this object layer by layer. And this is a very simple overview of it. If we move into a more detailed explanation of the same process, you can see it starts to become more and more things that you need to take into consideration. And I think to just highlight, this is a quite complex manufacturing process where the manufacturing of the single part itself is just a step of the way. It actually, to use this as an industrial manufacturing method, you need to look at the entire chain end to end, all the way from your materials to how you actually verify and certify your component if you want to use it in an industrial environment. And it's very easy to get caught up in the manufacturing box and focusing on the manufacturing aspects. It's actually, this is the technologies that are then hidden under the name additive manufacturing, which is today a standardized term by ISO and ISTM. And I'm not going to go into all of these, but it gives you a notion of the variety of manufacturing technologies when we're talking about additive manufacturing. And today we will be focusing very much in this area around a specific manufacturing technology that has been, I would say, an enabler for different industries, where I believe Siemens and NASA, who are here today, are great examples of how this can be sort of gone about. And what do we see then? I mean, what's the trend if we compare this to conventional manufacturing spaces? I mean, I'm showing here an example of how a facility working on additive manufacturing could look like. This is actually a Mexis facilities in Karlskoga, but it also showcases that the technology is moving from this sort of traditional dirty way of manufacturing parts. Of course, it's a manufacturing method with its own dirty little secrets, but it's definitely changing the game in how we manufacturing more advanced applications. And I think that is about it, what I wanted to talk about. I mean, but on behalf of Amexi and all of our owners, I just wanted to thank you all for coming here today, and I'm hoping that you're gonna have a really nice time. And it's about time that I introduce our moderator for today, Adam Edström from RISE Acreo.
Thank you, Edvin. Okay, welcome. We have a wonderful morning ahead of us, and we have a great crowd here from representing a lot of different industries, a lot of different universities and scientific communities. We have engineers, we have managers, we have some students, we have some people from the government authorities, we have some journalists. So welcome everyone. My ambition is that this should be an interactive event. So please raise your hand when you if you have a comment or a question or would like something clarified. Please make yourself heard. I'll try to, or make yourself seen. I'll try to get your word on stage. There is a program for today. That's my name. But there is also today's program, which will come here. Yes. So the day is divided into, or the morning, I should say, is divided into 3 sections. First of all, we'll hear from NASA how NASA has tackled some of the opportunities and challenges with additive manufacturing. Then we'll have coffee, very important. NASA is also very important. And after the coffee, there will be a section about how Sweden should do this. I mean, how should we actually go about to make the most out of these opportunities that are around? And we'll hear some different perspectives on that. And we'll conclude with a panel discussion where some of these topics will be dealt. We'll dive into some of these topics a little deeper. And after that, it's time for lunch. So without further ado, we'll hear from Brian. Doug, Brian, who is the first? You're going to go first. Okay, very good. Welcome, Doug, from NASA. I mean, you are, if I could introduce you very briefly, you are an engineer who spent a lot of time in NASA.
Correct.
Correct, yes. And you've done a lot of things with AM.
Correct.
Correct. And what? Because I forgot my little name, my little presentation from you. It's sitting right over there. So you have to introduce yourself.
I can do that.
You can do that. Okay. Thank you.
All right.
Welcome.
Thank you. Oh, great. Yes, my name is Doug Wells. I'm from NASA at our Marshall Space Flight Center, which is located in Huntsville, Alabama. We'll talk a little bit more about the structure of NASA and how AM is being utilized by NASA here in a few minutes. But I wanted to start by certainly extending a thank you to Amexi and Eva for inviting us to take part in this seminar. It's quite an honor for us, and we're quite pleased to be here. So thank you very much. So let's see. Figure out where I'm going to be to talk to these slides. This is an overview of what we hope to talk about. I'm going to speak for a few minutes, and then my colleague Brian West will come along and speak after me. And we're going to try to give you a brief idea of what additive is being employed by NASA and how we are working to develop additive to meet our mission goals. We'll talk a little bit, well, more than a little bit. We're going to spend some time on technical standards that have been developed at NASA, particularly at the Marshall Space Flight Center, so one segment of NASA. And we're going to talk about that as a framework for how we have been trying to tackle the problem of qualifying additive manufactured hardware for critical applications. So trying to bridge that gap between how do we just produce parts in an additively manufactured sense to the level of how do we produce parts in a production environment and produce them with a quality control scenario that we feel we can employ them in safety critical applications. So that's kind of the objective of our review of the technical standards. And we're going to use the format and the concepts of those technical standards to kind of guide our discussion. And within those technical standards, we'll talk about qualification concepts, foundational controls, such as what we refer to as a qualified metallurgical process, and how we accommodate understanding material properties in additively manufactured parts. And then we're going to hand off to Brian, and he's going to talk about the part production process and what we consider, how do you qualify a part production process. And then we'll wrap it up with some observations, some of the challenges we've seen, and closing remarks. But please, as Adam said, ask questions anytime along the way will be good. So NASA is not a homogeneous environment. NASA is a facility with, or an agency with 14 primary facilities, and they govern, or they are working in areas that are across the board relative to space and aeronautic sciences. So we have what we think of as our human-rated spaceflight centers, and those are the ones that most have likely heard of, such as the Johnson Space Center in Houston, and the Kennedy Space Center down on the Cape where launches occur, and our Marshall Center is located here in the South in Alabama. Space sciences world, so we have the JPL. Most people are familiar with the JPL guys. The Goddard Space Flight Center is up in the Washington, D.C. area. And these are the guys who do the really fun planetary science work and that kind of thing. And then there is an aeronautics wing to NASA. So we have a Langley facility that here in the Southern Virginia, a Glenn Research Center up in Cleveland, and the Ames Research Center out in California. So these guys are working aeronautics types technologies. So what that leads to is a pretty broad diversity in technical cultures. You know, there's a very big difference between human spaceflight technical culture and aeronautics technical culture and that kind of thing, and what we perceive and how we handle risk. How do we deal with risk? How much risk are we willing to take? And that governs quite a bit about how we go working our additively manufactured philosophical approach. How cautious are we in that? So those cultures are broad across the agency. And so we are going to be, Brian and I work at the Marshall Center, so we're going to be coming at this today primarily from a human-rated spaceflight perspective. So that's our point of reference. So in the space-related missions relative to additive, NASA has broken down along two lines of thought. One we refer to as our for-space activities, and those are the efforts that are primarily used for access to space. So rocket engines, structural components for vehicles, those types of things. How do you get to space? And then there's a whole other line of work that's going on relative to the actual in space. So in the long-term thinking, it's the in space that we believe is probably the game changer for the far future in terms of long exploration missions to deep space and that type of thing. How do you take advantage of the additive manufacturing culture and the capabilities that brings to a design and manufacturing perspective to enable those deep space missions and allow for example, not trying to carry all the spare parts you need with you to a Mars mission, for example. But at the moment, most of our effort, certainly the work that Brian and I work, is in this for-space scenario. So things such as nozzle chambers, rocket parts, rocket engine assemblies, those types of things are prime examples for additive manufacturing, and they kind of lead the way. So these are the missions that we're working. There's kind of been a recent shift within the agency to return to the cislunar space, be working in and around the moon as a bridge to further exploration missions. So a lot of what we are working on currently, the Orion spacecraft, the Space Launch System, our commercial launch guys, all of these things are leading towards continued support of the space station and then onward to near-term efforts at the moon. So that's where those are the missions that our additive efforts are supporting. So at Marshall, we've been tinkering in additive manufacturing for the better part of 25 years. And so long before additive manufacturing as a term came about, at that time it was the key words were typically rapid prototyping and that type of thing. So we were working in that quite some time ago. I remember helping to string cables together from our Unix machine to a small machine from a startup company called Stratasys, who was getting started with their FDM technologies, and we were a part of some of that early work. So, but our objectives in additive are the same as most any organization who's trying to get their hands around what can additive do for them. It's certainly a matter of decreasing production times and costs. From our perspective as a certification agency, we have a lot of time that we spend trying to understand, well, how do we certify a part? I mean, what does it take to decide a part is safe enough to go fly? And how do we do that? And how do we do that in a standardized manner? So developing processes and characterizations, sharing knowledge, getting data together to promote a smart vendor base, and then obviously the standard work of additive in terms of designing well-optimized components and figuring out when is an appropriate application for additive. Not every part should be additive. There are times when additive is advantage. There are times when, especially at this point with the hype, there are times when organizations or designers jump to additive when they really shouldn't. And so we try to help with those decisions. So our motivation to get started in the standardization world was primarily the benefits that we were seeing to the laser powder bed fusion. That's the process that Edwin pointed out to you, where we have a powder bed that is being fused layer by layer using a laser source. We also use EB sources as well, but when we decided we needed to get a standard together, we needed to start putting a structure and a framework together, we decided, okay, we're going to focus on the laser powder bed fusion process in order to narrow the scope. The additive scope is so large. We wanted to narrow the scope, and this process represented a good 90% or better of the candidate parts and components that folks were looking at relative to introducing additive into our systems. So some of the current projects that we're doing that, NASA currently has a program called our Space Launch System, which is a very large, heavy lift vehicle, kind of based on some of the early shuttle components. These are extended boosters, shuttle heritage engines, and that type of thing. But it's a very heavy lift, on the order of or slightly larger than the Saturn V for the moon mission in the 60s. Our Orion spacecraft, which rides on SLS, which is our exploration spacecraft, and the Commercial Crew Program. The Commercial Crew Program consists of efforts by the SpaceX Corporation as well as Boeing to deliver crew to the ISS, to the International Space Station. So given these these groups were really interested in taking advantage of additive manufacturing to reduce costs. One of the biggest pushes in the Space Launch System vehicle is to reduce the cost, for example, of those engines. For example, those engines are those that flew on the shuttle. And if you recall, the shuttle came back. So that was a big part of the development and understanding of those engines. They were reusable engines for a returning vehicle. This particular vehicle, unlike the SpaceX vehicle, this vehicle is not coming back. So how do you make that engine cheaper? How do you make that faster and considerably cheaper is a very big motivation. So what we decided to do, we decided we needed to have some standards. We needed to have a place to start. We had to have a way to frame the discussion, right? And so in order to do that, we decided let's try to take our shot at putting together a standard. And so these two documents evolved from that. It took about 3 or 4 years to make these come to fruition. But they are two documents. One is what we refer to as a standard. It's our Marshall Standard 3716. And it handles things like policy. So that's where you look for information about you need to have a quality system in place, or this is how you handle material properties, or this is what you need to do relative to controlling your process, or providing a non-destructive evaluation level for hardware, or classifying parts, those types of things. In this document, the Marshall Spec 3717, those are more procedures. So that's our thoughts on, well, how do you what are the minimum requirements for calibrating a machine? Or how do you control your equipment in your facility? Those types of procedural type things. These are open documents. If you Google that phrase in either of those, they'll take you to a link that is the outward-facing website at NASA for standards, and you can pull them right down as PDFs. So I would encourage you, if you have interest after our discussion, or would like to add them to your growing additive library of standards, then we'd be honored to have you do that. So there are a lot of topics that we could discuss relative to additive and the certification of additive parts here. We could have a week-long seminar easily if we wanted to do that. When Brian and I were trying to decide what would we best like to talk to the audience about today, we decided let's focus on things that are kind of core to the process, that are somewhat part agnostic. In other words, they're not, we're not getting down into the details of what would you do with this part or that part, but they're very fundamental concepts. And we chose to work on the concepts that we find least covered by the industry standards that are developing. In other words, the things we're going to talk about today are items that we have found in general, the ASTMs and the SAEs and ISOs have not decided to tackle yet. So those are some of the things like material properties. How do you deal with keeping that sorted and that kind of thing? So we're going to talk about the idea of how to qualify a metallurgical process, integrating an understanding of material properties and control of that process together, and how you take that kind of triad and work towards a qualified part process. And that will lead you to rationale at a core level for how do you qualify an AM part. That's kind of that's the roadmap that we're taking. We can draw other little circles, satellite circles around each of these, and we could spend a day working on each of them. Right? We could talk about the qualified part process and the scope of NDE or computed tomography inspections, and we could do the whole seminar. So we had to choose something. This is what we choose. We're going to kind of return to this graphic as we go along through our talk. Yes, sir.
So do we need to understand all of that stuff before we can use additive manufacturing sensibly?
In our opinion, before you go to a point of introducing additive parts into a system of value, or certainly a system with safety implications, our answer is yes. You need to understand that. These are concepts that are fundamental to the safe and proper implementation of additive. It doesn't mean that you have to have all of this information and sorted before you begin your development and your research in additive, or begin producing parts, or begin doing development activities. We don't mean to imply that at all, but by the time you're ready to take a part and put it on a vehicle of some form, or apply it into service where it has ramifications, yeah, we believe you should understand these things. Does that make sense? So we won't, don't feel that you need to be able to read and see everything that's going on this screen, but these are flow charts that are in the beginning of the NASA standard, and we're going to broadly use this to guide our discussions this morning. The first part of the discussion, or my discussion, is going to be on these, what we refer to as foundational process controls. And so these are things that I've mentioned before, where we talk about qualification of metallurgical processes and try to wrap our arms around how do we deal with material properties and additive, as well as things such as equipment control, quality management systems, and overall plans. And then Brian will take you through kind of the second half of this process, which is kind of the traditional design process as adapted for additive. So you'll find a lot of things very familiar here in terms of pre-production articles and manufacturing readiness reviews and qualifying of processes and that type of thing. But Brian will step you through those. So general requirements and foundational controls. One of the things that we have found that's kind of crucial if you're going to be establishing an additive process at your company, or on a given product line, and say, okay, I'm going to produce this part, and I want to be able to go fly this part or put this part into service. Having an understanding of how am I dealing with additive in an overall sense is very important. Having a framework In other words, what we think of as a control plan. And that, in the response to our documents, it simply means that you go through and you demonstrate in your control plan that, yeah, I've understood the requirements and this is how I plan to meet them. But in the larger sense, it's primarily a documentation for your organization to say, this is how we're handling additive. This is what we're doing in additive, and this is our policy, so that policies can stay consistent and engineers can know what the framework is that they're working within. Quality organizations can understand what their role is and how all of these things interact. So we think that having a control plan is a very important item. Equally important is having a quality management system that is well integrated into what you're doing, both at the engineering level, at the production level, etc. So in our flow chart, we kind of show quality and this control plan as big overarching entities. And so having a quality management system in place, again, we could talk about that quite a bit, but let's just say here, that's a critical item. If you miss the quality, if you have a hole somewhere in your manufacturing process where your quality management system is not keeping up with what's going on, you have a fundamental problem. So that needs to be an overarching concept. Equipment and facility control plans. We're going to talk about these two little boxes here. Again, we could spend a long time. We're not going to talk about that today, but it's a huge topic in the standardization world. How in the world do you calibrate these and qualify these machines? How often do you evaluate them? What exactly is an appropriate maintenance schedule for an additive machine? Those types of things. We require that you have a plan that states, hey, this is my policy for doing it, because at the moment in the standardization world, there is not a clear answer for that. Each organization is kind of figuring that out on their own. And from a NASA certifications perspective, we allow that. We just have to know what it is. What are you doing? And if it doesn't make sense to us, we'll push back. But we have to know what you're up to. Equally important in that is training. Training the workforce in additive is another big deal. That's lacking. It's kind of a fundamental enabler, I think, that if we get some standardized training processes in place and understanding of what does it mean to have certain certifications in additive, then that's going to be an advantage. So at the moment, we require that organizations do state clearly, how are you doing training? How are you training your people? Why is that guy competent to go push the buttons and change the powder machine or what have you? And make sure that they understand, whether it be the safety, the occupational safety concerns, which is an important topic for MEXI and their research agenda, but also, are they properly equipped and knowledgeable to do the operations that people are asking them to do? So it's very important that there be a training scenario in place. This is where we're going to spend a little bit of time here this morning. This is this green box that we've outlined here in this flow chart represents our approach, and what I want to be careful to convey here is that this is indeed our approach. There are a lot of different, we're not advocating that this is the approach or the only approach to doing this, but this is the approach that we've decided to take in order to qualify an additive process in this laser powder bed fusion scenario. So what we come up with is we define a metallurgical process. So again, when it comes to powder bed fusion, there are metals, certainly, and there are non-metallics and such. This standard is a metallics standard. Most of our work for our critical structures at the moment that Brian and I spend a lot of time with are metallic. So let that be known. We do, in fact, work quite a bit with non-metallics for other types of systems, particularly in spacecraft and that type of thing, for making lots of interior spacecraft structures and ventilation systems and that kind of thing. But our concept of discussion today is going to be in the metallics world. So we have this idea of we need to establish a candidate metallurgical process. Say, this is what I believe the process should be. And it's going to be a part agnostic process, and it's going to be a fixed process. That is some of the core concepts that kind of evolve based on the state of machines at the moment. In other words, the machines operate based on a set of parameters that are given by the operator, and the machine executes that same set of operational parameters throughout the building of the part. And that's a fundamental concept that's pretty important to us at the moment, because that's how we feel confident that we can understand the process, because we ask it to be consistent. We ask it to do the same thing each time. There's some complications in that, because you have to evaluate, well, if I ask it to do the same thing every time and not every part is exactly the same, is it always appropriate for any given part? And so that will come up in Brian's talk and how we establish that. But the idea is to say, let's come up with a metallurgical process that's based on 3 core items: the feedstock going into it, the fusion process, that's all the parameters we just discussed, and then the post-build thermal process. So those are the three core items that we think of as an additive manufacturing process, or metallurgical process for additive. And so once you've established, okay, I have a spec for my feedstock, I've come up with a set of fusion parameters that I like, and I have a thermal process that I believe can evolve microstructure after building the part, then I've established a definition of my metallurgical process, and I can go try to qualify it. So that's the idea, and this is an enabling concept for us, the way we think of this, because having these items defined and qualified and having metrics against them, that's what enables us to work the other problem areas, such as machine qualification and requalification. How do you set up process control metrics? How do you come up with design values for your engineers to use to put into parts? So we consider this to be a very kind of enabling and fundamental concept. So we'll go through those 3 core pieces very quickly. Feedstock controls. There's a lot of work going on in how do you understand powder for powder bed fusion type processes. At the moment, we've taken kind of a loose hand on that and said, we have a number of things that we want you to control relative to your feedstocks. We're not going to tell you what those controls have to be per se, but we say you do have to, for example, understand how your powder is being manufactured, chemistry controls, particle size distributions, morphology or shapes of particles, blending and doping controls, cleanliness, contamination, how you package it, label it, environmental controls, what you do relative to reuse if your environment has reuse of powder and that kind of thing. So we have these controls in place and require that fundamental core piece to be defined and fixed relative to that metallurgical process. The next piece in our candidate process is, how do you come up with the fusion parameter set that you believe is going to work? So there's an image stolen from Fraunhofer that's similar to the one Edvin showed relative to the powder bed fusion process. So how are you setting power of your laser, scan speed, all of those types of things relative to your process? And what's most specific about our metallurgical process is that we tie this all the way to the serial number of machine. Okay, so it's not generically, oh, I have a make and model of this machine, so therefore I come up with a set of parameters and I can dole it out to anybody who happens to have one of those machines and assume that I'm good. We don't do it that way. We have a candidate process, and then we qualify each machine by serial number. So those fusion controls, there's a long list of things that are in it. Everybody is, folks are likely aware that the quantities of settings that are available relative to this scenario are scores. can be hundreds or more. But they also have other things that are important, such as how are you controlling the environment in your chamber where you're doing your work? It's a welding process, so environment is quite important. Ventilation considerations. Brian and I have been tripped up by ventilation problems probably as much or more than anything else. And that is, how are you ventilating the bed where all of this process is going on? Because some of the alloys that we work in have a tendency to produce a good bit of soot and stuff, and it has a tendency to interfere with the power of the beam getting to the bed, creates defects and causes problems. So things like ventilation, quality of the gas, all of those types of things are very important. And we put those together into one box that we call our fusion controls. And we ask that all of that be well defined and well locked down. The other fundamental concept behind the fusion controls that I wanted to spend just a minute or two on is that the concept that we're relying on at the moment is that the additive machine works on the idea that I specify a power, a speed, a layer thickness, a set of parameters. I may have multiple sets of parameters. In other words, I may have a set of parameters that are used when the machine is making the outside surface of a part, and a different set of parameters when it's filling the inside to fuse the solid, make the part solid. But it's still a fixed set of parameters for different conditions. In other words, I know what they are, and it's going to do the same thing each time. And so what I need to do, though, is I need to keep in mind that not every part is the same. So those parameters need to be what we think of as well centered in a process box. So in other words, if that X represents where I'm going to operate my machine for a given set of parameters, I want to make sure that when I declare that my process, that if this red line in this kind of pseudo process space, so these are various and sundry different parameters that might change the process from being hot, such as where it has high energy and may lead to things like keyhole porosity or overheating and burning, versus cold down here where I have lower energy and might lead to lack of fusion defects. I have this box, so to speak, let's call it a parameter box. And I want to make sure that when I place my set of parameters that are functioning, it's well centered within that box. Let's think about it that way. In other words, I don't want to have, maybe I can do a set of parameters sitting right over here on the edge, but then if I have a geometry in my part, say it's a part that has very heavy sections, where the laser is going to be spending a lot of time in local areas and heating things up, then there's a chance that even though when I qualified the process it looked good, when I did my part it wandered out. I don't want that. I don't want that at all. So what I want to have is I want to have a process that's well centered in this box so that it can tolerate a number of different part geometries and scenarios when I'm building, so that my qualified process is as robust as I can have it. So that's the other idea that I want to get across. Brian is going to talk briefly about the idea and some of the challenges of very interesting work that's going on in kind of the final goal of a lot of the additive developers, which is in situ process monitoring and the ability to real-time control processes. We're excited for that, but it represents a challenge to us, as Brian will talk about, because then when I work this way, I can qualify processes. I can say, okay, there's my X. I'm going to put that there, and I'm going to make sure the machine's doing that, and I'm going to check to make sure my parts are good coming out. When I start letting the machine do things, now I'm in a different scenario. I got to qualify the algorithm. I got to say, why is that algorithm smart enough to do the right thing on every part? And that's a different process. That's a different, and in my opinion, a harder question to get to. So that's important to keep in mind relative to our ideas, that we work on a fixed process, and that we work hard to make sure that that's centered in the box. And then, as Brian will discuss in part controls, you got to go back and verify that on any given part that you come up with your approach to build an additive. Yea, verily, where I chose to operate produced the part as I intended it to. So there's two parts to that. Thermal process, just very quickly, we are not fans of putting parts into service with the microstructure that is created by the additive machine. So our idea is that microstructures that come out of the additive process that have these types of interesting features. We have another picture coming along soon, but you can see literally weld beads and crisscross and all that kind of thing going on. Very complicated, often non-equilibrium microstructures. We're not a fan of putting those into service. And so we have a generic requirement from our thermal process. We consider it core to the metallurgical process is that you're not done when you finish building the part. You've got to have some kind of way of evolving that microstructure. How do you move that microstructure from this very perhaps residual stress, high residual stress scenario with segregation in elements and all of that kind of thing? How do you move that to something that is more appropriate for service conditions? And so we consider that to be an important part. So once we've established it, what I've told you about are the core pieces of what we think of as a candidate process. What you got to do is if you get the candidate defined, your next step is to qualify it. How do I qualify it and decide that that process is actually good? So we have maybe 3 steps to that. One is metallurgical qualification, and that has to do with understanding how good am I actually building material at the metallurgical level. Do I have consistency throughout my build area? If my build area is, say 200 centimeters square, how do I know that all of those areas are producing material of equal quality? Understanding, like we discussed before, tolerance to variation. In other words, I don't want to qualify my process where I can build little cubes, great, or I can build a tensile sample, great, but I can't build a thin wall, I can't build a thick wall or whatever. So we've got to understand, can it tolerate variation? There are a lot of interfaces in additive parts when you get down into the understanding. For example, I talked briefly about contour passes, which are the passes that the energy source will make around the outside of parts to create a surface. How you have the interface between that and your fill areas, that's very important. It's a great place for porosity or defects. But certainly things such as if you have a machine or a part scenario where it requires a restart of the process, that's a critical scenario that's got to be qualified. Methods of filling, whether it be EOS uses the term striping, islands are used in some of the concept laser machines, where the machines are quickly moving to the point where we're going from a single laser to multiple lasers. And so now you got the concept of are the lasers going to share the burden? And if so, how do they negotiate that? And do they negotiate that well? And do you end up with problems? So all of those types of things are important to us from a metallurgical quality perspective. Second, sometimes you can build really good internal quality, but if you're not rendering a part nicely or to the needs that you have in terms of rendering detail or providing a nice surface to work from, relative if you're going to have as-built surfaces, or if you're going to improve a surface but not necessarily machine it away. You've got to have some way of working to understand and qualify, do I believe I have a set of parameters that are providing good surface detail and surface texture and providing all of that? In other words, are you building a part of the right quality? And thirdly, if you're qualifying this metallurgical process, you've got to understand the properties that process renders. So by the time I have built my material, I've ensured that it has good metallurgical capability. I have provided that it provides a good surface and detail resolution. Then you got to decide, well, hey, does it have the properties? Can it actually do its job that it is meant to do for a given part? And how do I figure out what those capabilities are to convey that information to my design community so that the design community can understand what their capabilities are, and that we can ensure that we've qualified a process that can meet or that can survive the environments that we ask it to. And in order to do that, we focus very hard on this idea of a material property suite, and it's a little bit new. It's kind of it's not a new concept by any means, but trying to integrate these concepts is a little bit unique particularly to a lot of the metallics world. It's not that unique if you're talking to the composites guys who work in process-sensitive materials and realize that, yeah, things might be different each day if I'm not careful. They're kind of used to dealing with it. But what we have decided is that we need this kind of material property suite. And the idea is that when you're registering your process, when you're registering your candidate by having it qualified, this registration process is how you demonstrate that the properties that are being produced by that process make sense relative to my design values in my bigger space. So that's tying things together. So the material property suite, the way we've devised it, and again, I'll throw the caveat out there, this is how we're working the problem. It's not the solution, but it's how we're working the problem. And it is, this is a scenario that, again, we find that the standards community thus far is not tackling. There's a material property community within the United States that handles the development and standardization of methodologies for materials for aerospace applications, which is wrestling with it, but that's the only organization that I know of that is actually trying to work this. Generally speaking, this is worked internal to companies, and the degree and the rigor to which they handle it kind of tends to vary with the culture of the company. So, but we have 4 items in there. We have basically a data repository. So that's where we have all of our data sets. We come up with a set of design values. That's a core piece of this suite. This idea of a process control reference distribution is pretty critical. That is, how do you understand what the nominal in-family behavior of your additive material is? And that's going to be a decision maker for keeping processes in check and understanding and supporting the rationale for using a given set of design values. And from this reference distribution, we set statistical process control acceptance criteria for witness testing and other purposes. So that's the idea. So the data repository, that includes data from all kinds of places, whether it be qualification testing when you're building up your fusion process and you've locked it down and you're saying, yeah, I'm qualifying this process. You have all of that data. You have material characterization activities that go on explicitly. So you need things like crack growth rate curves for particular material. You're not going to invest in these types of things until you have a qualified process, ideally. We see that turned upside down quite frequently, where we see people generating all of these types of data, fatigue data, crack growth rate data, and you ask a general question going back, say, well, how did you qualify that process? Why do I know that process is good? Why is that data good? And they're like, well, we didn't do that. We just started characterizing. And so then you kind of start backing up. But you get this data from a lot of different places, what we refer to as pre-production article evaluations. That's an important source of data, because that is taking data literally in situ out of parts that you have created. So that helps you understand this correlation between coupons that I do in this generic material characterization versus, well, what was the quality of the material that actually came out of the part itself? Are they actually the same? So that correlation is critically important. The other aspect to the data repository is it gives you the data necessary to set your design values. You want your design values to be reflective not only of characterization data that came from coupons, but you want to make sure that those design data are appropriate for that represent data coming out of parts and other types of scenarios, other types of geometries. It's a process-dependent material property. It can be. And so we try to minimize that through this metallurgical process that we described, but you still have to understand how do those properties vary. And so by incorporating data from all types of sources when you're setting design values is the approach to do that. The repository also gives you the data that you need to understand how do I do this equivalence concept. When we say equivalence, we mean I have a set of properties that I'm generating from my new machine that I got in, and I'm qualifying it. How do I decide whether or not those properties are appropriate to use in my design space, and that all of my design values I've made prior to that apply? We've got to have some way to do that. We can't restart our efforts on design values every time you roll over a software version or a new machine rolls in. Additive technologies are moving too fast to do that. So the idea of coming up with equivalence measures is very important. And so those are basically just statistical evaluations to show equivalency between data sets. So design values from the data sets. They'd be statistically substantiated, typically down at this tail of a property distribution at the 99, 95 limits is typically where they are defined to lie. And we include all the applicable sources of variability when we're looking at design values. Like I said, from coupon data from pre-production articles, whether it be characterization data, witness data, etc. And quite often, if you're smart about it, you're not going to, at this point in additive, you're not going to tune that right to the edge. You're going to leave yourself a little bit of room for learning something new, because that's going to happen, guarantee it. The other item that we do is what we refer to as these process control reference distributions. And it's an important concept to us, and one that we're hoping will show up in some more of the industry standards. And that is, it's not terribly unique. It's basically coming up with some descriptor of this data, this larger data pool that says, relative to the witness coupons anyway, what does the process look like? If the process is in control, what does it look like? You know, what is the average value that it produces for a given property? How much scatter is typically there when the process is in control? Understanding what that family is very important to us. And 3 minutes? Okay, I think we're not too bad. Not too bad. The idea is that we want to have some idea of mean and scatter, so that when we go forward and we're producing parts on a daily basis, we have a way to say, yes, that process is in control. I'm looking at it and it is in control. It's in family with prior work. What we'd like to avoid, or well, let me cover this real quick. Based on that, that gives us this SPC criteria for witness testing. So in other words, what we're really interested in doing when we do our witness testing, and I'm kind of realizing now that I'm talking about witness testing prior to Brian describing some of the witness tests in the part process, but what we refer to by witness testing is having coupons in the builds that we are evaluating properties on. They could be any number of type of properties, but by far the most common is tensile strengths and that type of thing. But what we want to have is we want to have some meaningful criteria set to evaluate those. What we find more too often is that the acceptance criteria is tied to these design values or to some minimum number. In other words, they say, well, my guys are designing to this number X over here, so I'm going to pull a tensile bar. As long as it's greater than X, it must be good. So that's the concept that we are not excited about. Then that is the tradition, honestly, in metallics. Not as much so in composites world, for example, but in metallics, it is the tradition. And so we're swimming upstream against tradition and trying to require that. But what the problem that we have, particularly if you literally set it against a design value, because as we said, this is set way down here. It's a low, easy bar. But then quite often, for conservatism, we even add some pad to that from a design value perspective. And so what that means is my process can walk all over the place before I flag it. In other words, I can really move the mean of that population before I flag it. And so we don't like that. We think it's quite important to say, I know what the family of data is, and I'm going to watch my witness testing on an ongoing basis, and I'm going to plot that against it. And so it's the control chart scenario. It's SPC, Statistical Process Control 101. That's all it is. We're just asking for some of that to be incorporated. And you wouldn't think that that would be quite as big a deal as it is, but you would, yeah. It can be hard to force folks to do that because they're not interested in all of the logistics that go into that, and it's a challenge. So I've kind of talked to this slide a little bit ahead. So the idea is not to base our acceptance on these spec mins, but instead come up with, for example, an acceptance range on mean, an acceptance range on variability, maybe a limit on the lowest single value, and use that family to understand how your process is doing, not just saying, oh, it's greater than the green line, it must be good. So that's our idea. So what we've done here, we've talked about qualifying a metallurgical process, feedstock, fusion controls, thermal processing. Get ourselves a fundamental process that's producing material we like and that does so with flexibility. So it can do it not only in a cube or a coupon, but it tends to do that across a large array of environments, thermal environments, part environments, and that kind of thing, so that we have confidence that in general our process will produce good parts. Utilize the idea of understanding that process and putting it under control and tying the material properties back to that metallurgical process through what we refer to as that registration, and monitoring the properties through SPC. So we kind of end up with this triad, and that's how we decide we're going to keep our process in control, and we're going to substantiate a given set of design values that are in use by the engineering organization. So that gives us a few check marks on our checkpoint here. And what Brian is going to do, he's going to pick up and say, okay, how do I take this concept and move it into the real world parts? How do we take all of these fundamentals and start making real world parts out of it? So that is where we are. How are we doing, Adam?
Thank you. Thank you very much. Do we have any questions for Doug, or should we let Brian talk right now?
Either way.
We'll take the questions for both of you after Brian's speech.
Sure.
That's okay?
That's
Yeah?
fine.
Okay. Thank you very much.
All right, thank you,
Thank you.
Doug. All right, my name is Brian West. I'm the Additive Manufacturing Lab. As Doug showed, NASA is spread across multiple field centers, and even within our own organizations, we have a variety of groups who often don't have to integrate. So it's my job to make sure everybody's in the same room, talking and focused on the same product. So, because the products are where I mainly live, I live down here in this part production side of things. So we take all of that qualified process that Doug was just talking about, and we start to apply it to those parts. Starts off with the design process. So this is a paradigm shift for a lot of our engineers who have 20, 30 years experience designing for a CNC machine. It's a very different set of design rules for additive manufacturing and different per additive manufacturing technology. Now, you'd think that's fairly easy to get across, but we have a lot of people who try to shift to additive late in the game. So now you have a part that's already been conventionally designed, and they need to go back through and take these design considerations into account. And you have new tools like topology optimization, simulation, and things that can help you in that design process, and those are very new tools, so you have to go back through and kind of relearn how you do business. So once you get a part designed, we start with classification. And this is our attempt at communicating risk. And it starts off with basically 3 main questions. How bad is it going to be if this thing fails? Are you losing a launch vehicle, or is a set of cables going to hang just a little bit lower if the bracket gives away? How hard are you loading that part? Are you pushing it to its maximum, or do you have 10 times the strength you need? And then additive risk. How hard is it going to build? Are you pushing the max on angles? Are you going from really thick to really thin sections, pushing the thermal ranges of the parts? How hard are you pushing the systems? And that helps us quickly communicate that risk. And sorry, I didn't point this out earlier. We're kind of following along the flow chart right here. So for us, it's a risk communication tool. We have many partners, both in the commercial side and on launch vehicle side, and everybody has a different take on how much risk is too much. But our program guys who are buying those launch vehicles need to understand how much risk they're buying. So we were looking for a common communication tool. So each one of those check boxes, each one of those levels has a table in the specifications associated with whether you're high structural demand, how much you're pushing the technology. This is focused on powder bed fusion, so the rules for AM risk are kind of set towards that, but those can be tuned for different additive processes. So we can look at a A1 or a B2 and tell, all right, how it fell down that flow chart, so we can quickly communicate that risk. And part-specific tailoring does start with the classification, because if you have a highly loaded piece of turbo machinery in a hydrogen turbo pump, that's a very different story from that simple bracket. So how much will allow that tuning of the requirements really starts here. Okay, a lot of words on this chart, and I promise you I will not read them to you. But a lot of challenges started off right off the bat with this classification system, because as a disruptive technology, the very first people who wanted to employ additive were the science guys and the spacecraft guys. This is a manned space flight spec. So we were looking at liquid rocket engines first and foremost, but the CubeSat guys, the science mission guys, they called first and said, well, we have a smaller program. We don't have the resources to do all this. How can we tailor those requirements? And that challenged this paradigm of part classification. Now, early versions of the spec had a Class C, and from our manned spaceflight viewpoint, we kind of had our blinders on. For us, those were demonstration hardware, desk toys. You know, here we were able to build this. But really, that classification system needs to be for the science missions, and you know what NASA considers a Class D mission. So what we're in the future, what we're starting to work on now, is elevating these Marshall level specs to an agency level, and at that level, these specs will be broken into human rated, science type missions or Class D missions, and then the aeronautics guys will have their own version, because it is a very different culture for each one of these different organizations. So we'll be able to codify these different classifications at those different levels. So as Doug alluded to earlier, additive is a highly integrated process. What you do in design affects your surface finish, which affects your high cycle fatigue performance, which affects your design cycles early on. So I alluded earlier that people wanted to adapt additive manufacturing late in a program. That drives your design analysis cycle. So if you go to make a change, you have to redo all that analysis in a rocket engine. That's a very expensive endeavor. So you start running back through the do loop over and over again. So it's important to make these decisions early. So, and one of the other things that's bit us quite a bit, people say, all right, we can get this part into the design space. We need to figure out how to get the powder out of it. We need to figure out how to clean it out. Because if you have a blocked chamber and you cannot get the powder out of it, you end up with a block of sintered powder inside your part. Whether it gets wet or gets heat treated, that's never coming out of there. That part's scrapped. And you can make really nice, really cool coolant channels in a part, but if you can't get the powder out of them, you can't use the part. So you have to take all of that into account when you're setting up your process and setting up your part design. So we've had a lot of challenges as we've started to implement additive at NASA. And a lot of the requirements in the specs, I can look back at the requirements and say, yeah, that one hurt when it bit us. So our mistakes have often been codified into these requirements. But as we go through and start to set up this part production plan, it's kind of our integrated, how do you take that entire program, how are you doing this part, and lay it out end to end, cradle to grave. How are you processing that part to make sure you know if you have to, an area that's going to be hard to get the powder out, how do you get it out of there? How do you lay that out to make sure someone doesn't send it to an EDM before you get all that powder out? And one of the big challenges we were kind of surprised by was one of the things we asked for in that plan is an integrated structural integrity rationale. It's give us the short story of why you think that part is good enough to fly. Summarize your NDE, summarize your structural analysis. And getting people to do that succinctly and make sure they understand the rationale of why their part is good to fly. That's been a little bit of a challenge for people to try to summarize that, and rather than just say, my analysis is good, check that box. I'm able to inspect most of it, check that box. You know, making sure you have all that covered has been challenging for folks. So another one, because additive is so easy to make a change, everybody keeps making changes to their parts. But we encourage people to lock those build files and not change them. Because of little things like this, these little bitty hairs, those are stray vectors. So each time you reslice a file, things like this can pop up. And we've seen these pop up in very fine coolant channels and passages. You cannot get those out of there. That is in this case, a piece of nickel alloy 718. No air blast is going to remove that. So later on, we'll talk a little. Doug talked about a first article evaluation that kind of goes through. You cut up parts and you look for things like this. Once you reslice that file, you can no longer guarantee things like this haven't come up, and they've come up more than once because that's a copper alloy system. You can see a lot of vectors back and forth. Those parts aren't supposed to be connected. We still cannot explain how all these vectors got there. Just a glitch in the file structure when those slicing files were made. So let's see. We'll talk a little bit about the digital thread later on, but to control those files, we push people to try to use a cryptographic hash program to make sure you're using the right file. File naming conventions can change, things can be corrupted. You need to make sure you're using the right version of your file. And NDE has been a big thing for us because CT is a powerful tool for additive, but it's not certified that you can find a certain size blah. So you have to do it on a part-specific basis. So getting people to really go through and understand NDE before they start trying to put the part in the system is critical. For a lot of people, they've taken for granted that, well, CT will find any flaws that I can't screen. Well, maybe not, because we can take an injector with 160 pieces, make it into 3 pieces, but now CT cannot penetrate 9 different surfaces of nickel alloy. You just can't get there. So we push this first article inspection. Very similar to castings. You make your first one, you cut it up, and you look for porosity. That's similar to what we're doing, because a thick section has a tendency to have different porosity, perhaps different microstructure than a very thin section. So you need to understand those. Overhung surfaces have much rougher surface finish and can perhaps have overheating, keyhole porosity. So that plan is intended to go through, take that locked file, cut it up, look at your critical areas, look at thick, thin, look at fine channels. Are you getting what you think you're getting? Is the part sagging or warping? Do you have residual stress that has closed up passages? Those are the types of things you're trying to document in a first article plan or a pre-production plan. So we've kind of transitioned from this part production plan box to getting to that last circle, that qualified part process. So we take that first article plan, and once we've cut it up, we've done a report, everything checks out, it looks good. From there, we take all the stakeholders, pull them in a room. Does everybody understand the risk they're buying with this part? Make sure our program guys, our chief engineers, we all understand there's no holes, we haven't missed anything. So we get everybody together, review that data, and make sure we're okay. We call that an additive manufacturing readiness review. So once that's done, we lock that process down. That part is now linked back to that serial number machine. It's made with that QMP on that machine at that facility. And if you want to add a different machine of a different serial number that's not part of that QMP, you have to redo that first article plan to lock that process, because we have seen variation between a concept laser machine or an EOS machine. We do see differences in the way these parts produce, and that's important to understand to make sure you're getting the end product you think you're getting. All right, I know I blew through that rather quickly, but that gives us this qualified part process at the end. So that circle I put up earlier, it's a highly integrated process. Each part ties back to its predecessor and back to the very beginning. We have found things in a first article inspection plan at the very end, and we've had to go back to design, change a cooling passage size. That leads you back to another design cycle, which was at the very beginning of that loop. So it's not just something that we can just go to additive and do. We need to make sure that we close that loop as early as we can with manufacturing test demonstration hardware and other things to go through and really look at the hardware and make sure we understand it going forward. So we're through this. We're at this QPP state right here. So we have a qualified part process. We're getting ready to go into production. Now, as Doug alluded to earlier, with each part, we place in that build file high cycle fatigue tensile specimen, metallography specimens, little bitty parts that he showed, the little blocks with the features. We place all those in there, and that's how we monitor our builds going forward. And how different companies approach production is different from facility to facility. Some people have their own machines. Other people want to go to a vendor and only buy 6 parts from this vendor, and then they don't need to use that vendor for another year. You know, we're pretty low production rates in this world, so it makes it ideal for additive. But it challenges the idea of statistical process control when you're building 6 parts in one production run. So we've kind of laid out different requirements for those witness specimens. If you're only doing 6, you need to build a few more to make sure you compare back to that process control reference distribution. You have to look and make sure you're still matching. If you're in a continuous state, you don't need quite as many because you have a database that you're looking at, and if a machine is trending down, a filter's plugging up or something, you can see that in the data as it steps down. So we try to get people to compare that back to a control chart to look for that drift. So, but those intermittent builds really does cause a problem, because if you've been off a machine for a while, you don't know what that vendor has done to that machine. And we try not to, we personally try to keep a machine in an alloy system, because we've seen problems with cross-contamination in the data. You know, that will bring in some risks that we'll talk about here in a minute. So some of the challenges we face is getting those samples tested, and how do you flag a part? Because it may be several months down the road before you get that data back. And do you keep that, if you keep the parts with your sample, and or you keep your samples with the part, and that part has to go through machining, you know, you're just lengthening the amount of time before you find out that your machine may have a problem. And again, Doug alluded to setting those limits to monitor for that drift. So that delay is a risk. For us, it's around 3 months from the time we build a part till the time we get that test data back, because we typically separate our parts from our witness samples. So in that 3-month time, that machine's not sitting idle, you're building parts. So if you pull a sample and it fails your witness criteria, now you need to go back and look at everything you've built from that time on forward and start scrutinizing all of that hardware. So you run into challenges in an operational environment. How do you put a flag on the parts that says, hey, those witness specimens haven't been tested yet. That part's not fully, can't be released for flight. You need to pay attention and make sure you close the loop with those witness specimens. And if that fails, when did your process go awry? That's what Doug was alluding to. If you set your boundaries so low, you cannot pick up the drift, because if you pick up the drift, you can start correcting it before you start scrapping hardware. And that's something we've been bitten by, unfortunately. We switched alloys, and it was 6 months before we scrapped about 6 months worth of builds before we got that thing fully cleaned out. But at the time, it was 4 months or so before we saw data, and by the time we got it fixed, it's a big problem. So we try to watch for that. So a lot of the vendors that we work with aren't used to this level of process control. People who are like, well, it's just another machine. It's not quite at the level of a CNC machine yet. It's not that user friendly. They're not used to doing a lot of this process control, and I just don't want to do that. Well, you kind of have to, because these things shift, and they can shift quickly. Filters can plug up, ventilation systems can go awry, and any number of things can happen to laser calibration or laser power that you can't catch visually, but it will affect the microstructure greatly. And if you're depending on the alloy of your powder, reusing it can be an issue. Nickel alloys are pretty forgiving. Copper alloys, not so much. They're very sensitive to oxygen pickup, and so are the titaniums and aluminums. So you can't reuse that powder quite as much. Unlike a nickel alloy, you can run that in a machine for quite a while, but we're studying that right now. And cleaning is not trivial either. Because of the laser process and the heating, you get partially sintered particles hanging on the side. So you can clean a part, it'll check out fine. You clean it again, you see silting. Little bitty particles start shedding. So how you control that process, how you clean it, do you surface finish the whole thing? Do you do chemical milling or something else to etch away that outside layer? That all affects how you process the part, and in turn affects your high cycle fatigue properties, which loops you back to your design at the beginning. So you have to understand all of that ahead of time. So Doug alluded to influence factors at the beginning, and that's, you're looking across your entire build plate, not only X, Y, but in Z. Do you have any areas where you have recirculation in the gas flow, a smudge or a damage to a lens, or something the laser passes through? All of these can affect how the spatial property relationship of an additive machine. They're all things we've encountered. Fracture control and how you understand all that fracture data, that's something very near and dear to Doug's heart. And maintaining the digital thread has been tricky, because it's not only a CAD model and a drawing that goes to a tape for a CNC machine. Now it's a CAD model to an STL, to a Magix file or an Inventor file, to a proprietary file format for a machine, and then into machine code. So you end up with all these derivative files, and if a problem's ever found and you need to trace back through that, how have you maintained that file structure and that digital thread? How can you go back through and say, yea, verily, I know, I can find where something broke down? And that's not trivial, because you have so many more derivative files than you've had before. And that's even more complicated when you start dealing with a vendor, because now you are no longer in control of half of those files. Your vendor is. So depending on your relationship with them and how you control that intellectual property starts to play into that. Doug alluded to this one earlier, because we're doing as much as we can to help push this technology forward, because NDE cannot see all the way into an injector. AM enables such organic, complex, really cool structures, and the next leap in the use of additive will be being able to apply those advanced structures. And in situ monitoring can help. Thank you. Perfect. In situ monitoring can help get us there, because as Doug said, seeing into the middle of that part and knowing there's a defect down in the middle, that's an NDE process. We now know there's a defect there, and we have an idea of how big it is, so we know if it'll hurt us or not. Right now we can't do that. So when in situ monitoring is certified, qualified, we have faith in it, we understand it, we'll be able to use that as an NDE technique. But that is going to be a much different story if they start, when the machine manufacturers get to the point where they start altering the design process, because then it's almost like it's not a locked slice file. the machine can change the slice file on the fly to account for things it thinks it sees. So there's an entire machine control process that you have to understand, and that's going to be a much more complex problem. So that one's probably going to be, for us anyway, further out than being able to rely on a standard in situ monitoring system. So the final box, the fun part, is service. We get to go out and test stuff. Go out and try to break hardware. So we do a lot of work in the Glen research-based copper alloys, doing a lot of thrust chambers and other test hardware. A lot of success with LOX methane testing and LOX hydrogen testing out at Marshall on small upper stage engine class stuff. And we have done some ox-rich stage combustion testing. One of our good test bed programs out at Marshall for trying to teach our engineers additive, need to give them hands-on experience. So we have what we call an additive manufacturing demonstration engine, launched with the intent of try to build as much as you can out of additive, take a very, very high-risk posture, and see what you can do. See what you can break. Test it. And they should be testing that complete engine hopefully this fall. They've been breadboard testing components over the past couple of years and very successfully running that fuel turbo pump in both LOX and hydrogen and methane. So turbo machinery and turbine blades and everything made out of additive. So it's been a great program for our engineers to learn about the technology. So the process control, the in-process controls are very important to understanding what you're doing. You have your QMP, your part production plans. Those really help you understand what your process is. And we do things like a process failure modes effects analysis, trying to go through and understand how our process can fail and monitor that through the statistical process control as much as we can. And then in post-processing, we get into the NDEs and really inspecting these parts. Because right now we look at 100% inspection. Until we know more about the technology, until in situ monitoring comes online, we really want to understand if there's a rogue flaw, a rogue defect, or if something's gone wrong. And the reliability comes out of the cross-section of these and where these components come together. So by the time we circle back around, something way out here at the end as you're going into flight affects your QMP, affects your material properties and your process control. This is a continuous cycle, and that is a paradigm shift for all of our manufacturing. So thank you all for listening today.
I have a few questions. Could we please have both of you on stage, maybe, because I don't know which one of you will answer the questions. But so anyway, thank you both of you for great presentations. My impression is that this is not as easy as it sounds from the beginning, but maybe that's you've definitely done at NASA. You've done a great job in clarifying these processes and also documenting your findings in the two documents that you described. But in practice, I mean, in this room we have representatives from a lot of industries, a lot of companies who are on their AM journey somewhere. And yes, they can download the documents and they can learn a lot of things from that. What else could they do? Could they call you guys and say, "Hi, we really don't understand exactly how this is done," or send you an email or whatever? Are you open for that kind of discussions at all, or how do you get the deeper knowledge?
How do you get the deeper knowledge? Yeah, we have a lot of folks who call and ask questions, particularly about concepts in the documents or concepts like we discussed this morning that are not, they can be hard to, standards documents are not known as the easiest things to.
Maybe not the bedside reading of choice for everyone. No,
exactly. And so yeah, it's certainly something that that often requires time and effort to to dig into and really understand. I mean, we are always open to questions and comments and that type of thing relative to if there's any concepts that we can help with or we can answer questions. We're always open to that. But I think the key to it is actually getting hands-on. The key to it is actually trying to put all of the pieces into practice, step by step, one piece at a time. Start with your development hardware, understand how that works, and move that process step by step into a more production environment. And understand as you do that, bring in the necessary controls, and in other words, don't try to eat the elephant at one time.
No, I mean, get your hands dirty, do whatever it takes.
Right.
But then again, you have spent an awful lot of time. You mentioned a number of years and a number of $1 million that you had put into this development. Many of these companies don't really have that luxury or don't have that time or that money. What would be your advice to speed up the process for anyone who is a little bit earlier on their AM journey?
Go in with your eyes open and understand the integrated nature of
Okay.
additive. You can't look at it as just a manufacturing process that I'm going to push the button in a machine and a part comes out. Complexity isn't necessarily free. You're paying for it on the inspection side. So, and to go back to the earlier question, part of the reason for the heft of those two documents is there's a lot of rationale and commentary in there to help explain some of those things. So understanding that and then going through there knowing that it's all integrated will help.
Knowing that it's all
Going back
integrated
again.
means that you have to have a different mindset than that it's just a production technology.
You can't look at just design or just surface finishing. You have to know how everything interacts.
Which is sort of a threshold for many companies, as far as I have understood. Yeah,
It is. It's a challenge for some of the smaller companies to put all of those pieces together, because there are bits and pieces of expertise in additive that cover lots of technical disciplines.
indeed.
And the traditional way in which small companies or the larger industry at whole has tackled those problems is through standardization. In other words, you have standards bodies who come up, understand what are the challenges. They produce standards of methodology or standards of products, and that allows all of the entities to work from the same page. In additive, we're young enough that those standard products are still lacking.
They're work in progress.
They're a work in progress, exactly, and so they're progressing quickly, and the work of the ISOs and ASTMs and SAEs of the world are going to certainly help. I think that's going to be the key. But trying to understand, as Brian said, the full picture complexity of things that need to go on in additive, and doing that from the beginning is the key to avoiding large mistakes and having wasted efforts and doing things twice and so forth.
Good points. Questions? Yes, please.
I have a question about the parts that has been produced and once delivered to the customer. What kind of traceability do you have on each single part back to when it was manufacturing powder, batch, that kind of stuff?
In the qualified metallurgical process up front, that documents everything on the machine side down to powder lot, machine serial number. Through there, that's where we maintain that control of the process itself. On the part side, the digital thread has to carry that. That's where you're tracing which CAD file, which build file, and which slice file that part was produced from. And then once that part is produced, you get into where the quality management system picks up in a production environment of, did the quality inspectors buy off at all the right points? Do you have those right checkpoints in there that for standard three-dimensional inspections, things of that nature? So it's an integration of all those processes.
We do require at this point in time We require unique serialization of every AM part. It's been a debate that people have pushed back on, and we haven't gotten to the point now that, at least in any kind of universal sense, we're willing to let that go. But that serialization of the part back through the digital thread, as Brian mentioned, and the qualified part process and so forth, that allows you to tie everything together, everything from every file that went into it, the powder lot that went into the part, all the, obviously all the chemistry, date of manufacturer, all of those things should be tied together in that sense. And that's admittedly, that's a bit of overhead. That's and that's probably something that various industries are going to have to decide. How do we do that in an efficient way that's appropriate to our industry and our hardware? At the moment, it's appropriate to our scenario just because of the typical dollar value and effort that goes into the parts in our industry. But that's probably not universal across the board. So that's but I think for a good time, the analogy that's typically used is that each AM machine is actually like a small functioning foundry, or its own little manufacturing house, so to speak. And at least from our observations to date and the things that have screwed us up and so forth, we're not at a point now where we believe we could let go of that traceability, by any means. I think we're still too young in the process to not have that capability. So our requirements tie all that together, and you have to have that sorted.
Thank you.
It's overhead.
More questions? In that case, thank you very much, Doug and Brian, again.
Thank you.
In case you missed some of the finer details of Doug's and Brian's speeches, this entire session is recorded and will be on the IVA homepage eventually. We are now having a short coffee break, 10 minutes, so we will be back here at exactly 12 minutes to 11. Coffee is served right outside, and there are also bathrooms all the way down to your right. Back here in 10 minutes. Thank you. Right, ladies and gentlemen, please take your seats. We are about to get ready for our next speech, and our next speaker, maybe you do need an introduction. Christer Fuglesang, the only Swede who has ever been in space, who has actually used the stuff from NASA and other space providers to do whatever astronauts do in space. Welcome.
Thank you. Thank you very much. Thank you. This is, I must admit, the first time ever I talk about additive manufacturing. So, and I was asked to talk about the aim for space and Saab, and to be honest with you, it will be much more about space than Saab. But those who want to learn more about Saab is doing in AM, they should really join in Linköping tomorrow, because there will be several talks about that. I'll mention one thing though about Saab. But first, I want to take you on a little adventure to space and a story there which can give a perspective why it can be good to be able to do, let's see which one I do here then to get further. Why it's a good idea to try to do 3D printing in space. So this is actually when I'm launching on my very first space flight, 1 out of 2, in December 2006. And let's see this one. As was mentioned before, actually these engines down there, they were reused on the space shuttle, but now we use the final time on the SLS, and then they had to build new ones. It's a very powerful event here, some 2,000 tons getting to space and some 50 million horsepower, you can say, which you can point out. Someone brags about this new car with a few hundred horsepower. But anyhow, we were on our way here on a mission to continue building the International Space Station. At this time, the space station started to be assembled in space already in 1998, and from 2000 onwards been permanently manned. And it was more or less halfway in this build-up process when we launched here. By the way, this whole launch sequence takes only 8.5 minutes. That's how fast you go to space. Another 2 days it took before we docked to the space station. That's maybe more because we want to make a kind of slow approach and not go so fast. So on board were 3 people living there at the time. One was a German colleague of mine, Thomas Reiter there. And as I said, our main mission was to continue building the space station. That we did already the following day during the first spacewalk. So we had with us a piece in the shuttle, this one here, which was brought out with robotic arms to the end of the space station, and there we prepared it, and then we secured it in place using, among other things, these kind of battery-driven bolt drivers. However, the following day, we were going to retract this solar array with the help of commands from the inside. But, as you can see here, it didn't really work out as was planned. This led to a kind of a problem, which in particular the ground control had to try to think about. How can we solve this? So this is here a close-up picture of how it looked after many attempts to try to unfold it with commands from inside. We went in and out and didn't really work out. Now I can only tell you in a hand, the problem was actually these guide wires here, where some rings here, they didn't glide smoothly through. But that's a side thing. What I want to tell you is, what happens now? Well, it happens then ground control starts to figure out what can we do. And they have experienced astronauts, like here, testing in the training center, putting together what kind of tools do we have on space that could be useful, and see what can be done. And then they told us on board, hey, build some tools in space. Use these things here and put it. So I built this tool on direction from some ground, and as you can see, it's a lot of tape around here. That's insulation tape. That's because the solar array, when the sun shines, there's at 160 volts. You cannot turn that off if the sun is on. So we didn't want to get the electrical shock when we was going out there, and so that's why we had to have 3 layers insulation tape there. Even on our spacesuits, all metallic parts, we had to get that. And so with the help of this tool and some other tools we were made to make it worked out. Here you can see my Robert Kirby made the EVA with me. He's holding this tool, and here is how he's working on it. This fancy photo actually I took by mistake, I thought, because I was going to take a selfie when he was working out there, and then I realized, oh boy, I have my visor down. I'm stupid, I'm not seen, so I raised my visor and got a very bad picture. But this one here with the mirror effect, and you can see Beamer, they're working, using that tool to work on these wires so it kind of could be retracted, and then you see the little nice flag down there also. So, and here is the proof that it finally worked. You see here, this is the retracted. And the whole purpose with this was that the next flight they had to retract this one, and then this whole piece was moved over here. But that's another story. So you can see how good it would have been if we would have had a 3D printer up there who could produce a tool which we needed. And indeed, today we have that up on ISS, and it was actually even shown by Doug earlier. Let's see, how do I go back? This 3D printer called Made in Space is up there, and you have to keep it in a glove box. So if something goes bad, nothing comes out in the atmosphere. And here's one of the first tools were printed up there in 2014. Now, though, there are some problems having a 3D printer in space. First of all, everything is weightlessness. So anything works on Earth may not at all work in weightlessness in space. So you have to make a much more sophisticated machine. And then if you work with metal, it will take a lot of power, and all this power limited in space. But I think it is the future for space. Certainly when we go to Mars, you cannot bring all the spare parts with you, but if you can then just send up a CAD file and make it, then you're very much better situation. I want to talk about another thing which is now being made partly in 3D for space, because I happen to be part of this. This is an experiment which I'm working with at KTH. I'm also working, and it's a small experiment which will be put on the International Space Station next year. Looks like that, and several of these parts are now being actually manufactured by 3D printing. What we're going to do with this experiment, well, it's actually to test some new technology and methods for studying high energetic cosmic ray in the future, but we can also study things like meteors and high altitude lightnings and other things, UV phenomena basically. But that's not important right now. So it was figured out by the guys in Rome, who's part of this collaboration, who's producing the mechanical housing to this experiment, that, well, it would be a good idea to use 3D printing for some of the parts. And this is, if you see here now, that these pieces basically are the ones which have been 3D printed. And why did they do that? Well, it kind of particularly made the weight lighter, and it also some not so easy geometries to make, so and using 3D printing was better. And now this is a one-off thing, so you don't have to maybe following all the qualification steps, which NASA was talking about. You do one, and then you make sure that it works, and that's good enough in this case. They used Ultim as the material, which is the strongest you can have apparently, if you use this method called fused deposition modeling. And well, I'm not going to go through how it works, because I think everyone knows that. But at least it's another example of how you can use 3D printing to make things for space. And here is how it's now being these parts has been 3D printed and being mounted. Then it had to be made in black eventually due to light tightness. So another example for how you can use 3D printing for space experiments is not really that you want to maybe send it to space, but for other purposes. So this is a student satellite called MIST, which is currently being made by students at KTH under professional lead of Sven Gran, Mr. Space in Sweden. He is retired as CTO at the Swedish Space Corporation. And every semester we actually have a new team of students who continue working on this. And it's a challenge indeed. And another challenge is that we actually have 8 what we call payloads, experiments, or demonstrators on this little satellite. And to get everything in this fit together is not easy. So as they say that one picture is better than 1,000 words, well, one 3D printed model is better than 1,000 pictures. So what they've done is to 3D print all the experiments, and here in the middle you have all the systems for the satellite itself, and then see how it fits together. Now they're working on how can you put all the cables and to get everything connected as well. So this is another example of the usefulness of 3D printing when you're going to space. And also makes a nice model to show people. So you can have a look at that later. So I'm not going to go through all these experiments, what they are, but they managed to fit in here miraculously, actually. So what is Saab doing then? Well, Saab uses AM more and more in various areas. And I'm just going to show one successful example here, which is being done, used at Saab Surveillance, and Martin Blinius there will talk about this tomorrow, and thank you for providing me with these pictures. So they needed a new heat exchanger at the antenna assembly on Gripen, and they needed quite many, and to solve the heating problem. This is basically how to cool this thing, if I understand it right. So they figured out that additive manufacturing using aluminum was the way to solve this after the various other things, and it even led to new patents. So they really improved the cooling performance. They also reduced the weight. Weight in space is very important, but even aircraft is important. So there was some very good steps forward, and now it's in manufacturing. Here you can see manufacturing many at the same time. Here's some other examples of 3D printed parts used in various areas within Saab surveillance, Saab aeronautics and dynamics, other business areas also using 3D printing. So I think somewhere in here, is that somewhere there, the one which we just looked at will fit on Viggen. Now I will finish by going back to space, actually going back all the way to moon. We are finally, I would say, talking about going back to the moon again. We will use the International Space Station at least to 2024. My guess is another 10 years. But discussions are now increasing and even being somewhat more detailed. How can we go back to the moon? And the current idea is to build a small space station called Deep Space Gateway, put it in an orbit, far orbit around the moon, and from there start with doing excursions down to the moon. That will not be permanently manned, but kind of manned for time to time. It's worth noting that no one has been on the moon since this photo was taken. Apollo 17, December 1972. And next year we celebrate the 50-year celebration of the first moon landing, which will be a big space year. Now, but going further, to build a moon base, well, how can we do that? And now there are plans being developed that, well, smartest way to do is to send robots there first and use 3D printing to build a moon base. So these are plants being developed. You try to do the chemistry right now so you can use the dust or sand, whatever you want to call it, the regolith on the moon to produce blocks so that it's 3D printing blocks. And then you use robots to build some kind of a moon base or moon village, which is the name which has been created by the current general director of the European Space Agency. A kind of symbolic how everybody comes together in a village. And eventually can build there. So here's another future idea, but I wouldn't call it science fiction. It's a kind of visionary there, but I think this is the way how it will be done. And then when we learn how to do that on the moon, then we are ready to go further and do it on Mars. So thank you. I don't know how much time did you ask me to cut down a bit, so I tried to speak fast.
Thank you so much, Christian.
Thank you. Thank you. Okay.
Yes, we will have questions, opportunity to talk to Christer more during the lunch break. But from now, from this sort of out of space applications to something very much more concrete, very much more in Sweden. One of the companies that has done the most and has reached the furthest on its AM journey is Siemens in Finspång. And we have the pleasure here to have Vladimir Nawrocki here, who is, I would say, the man, myth, and AM legend within AM in Finspång, within Siemens. So without much further ado, please, the floor is yours.
Pleasure to be present in this event, and especially to take a speech after the man who was on this space already. And this is where we believe this is one of the future for this technology implementation. So what I'm going to share with you, our experience in the area of the additive manufacturing we face in small town Finspång, in the company which called Siemens, but we have a quite long history. Before it was a ABB, then it was Alstom, now it's a Siemens. But the people, the team is still the same. So we're joking usually when there is a question why you guys are so, let's say, successful in this area. We are saying, but we have a very nice environment. We have a forest around, and we have nothing to do rather than be innovative. Yeah. So, and this is what I would like to share with you. Also, my task for today is that you will not bring some kind of wrong message from here that additive manufacturing is something simple, just push the button. But my colleagues from NASA did a great job. They already did, let's say, show you that additive manufacturing is not a simple issue. It's a lot of knowledge behind, and in order to be successful in this technology, you really need to keep your hands on this and then take care about the whole process, starting from the powder, going to the process parameters, going to the material qualification, going to the printing, going to certification of the materials and then components afterwards. And then there was a question also, tracking of the components which will be delivered to the field. This is what we need to do and close the whole loop. And this is a, let's say, way really to be successful, understand, and be quick. I also would like to share with you, let's say, our experience and then how we start with this technology. So I believe I should go here. So this is our way forward. So in general, with the additive manufacturing in Siemens organization, we're working more than 25 years. We did start with the plastic application, but the first application and thinking about the application of the metal was done in the 2008 when we found that this technology is really quite important technology. And at that time, I already was working in the service organization, and we found just to be flexible with our response to our customer, to provide the spare parts, to provide the components, to do repair in time, this technology really can help us and support us very much. So this is why we said, okay, let's pick up this technology, let's start to work. And due to the fact that we have in the big organization like Siemens, like GE, there is a, let's say, split of responsibilities. We have a special team who is working with the design. We have a team who is working with the service. And as I already said, I do represent the service organization. But when we came to our designers and say, guys, take a look. It's so nice technology, everything positive there. So, and the questions as usually came more or less what our colleagues from NASA said. Do we have a equipment which is certified for the serial production? We said, no, there are a lot of, let's say, pilots coming to the market. Do we have a powder which is certified for the production? No, we are working with this. Do we have a process parameters? Do we have materials? We said, no. Do we have design criteria? No. Do we have design tools? No. Get out. So this was the answer for, let's say, our attempt to start to work with this stuff. So we, together with corporate technology, we have a huge organization, research organization in Siemens, more than 4,000 guys. But researchers is researchers. Pull here, see how the system will react. After like 2 years, we found that the metal is still like a glass. So it's not a metal, it's a glass. So we found, okay, in order to understand, we need to get in, we need to put our hands in, and we decided to buy the first printer. So it's what was recommended by Brian. Yeah? Take a machine, start to work. And then afterwards we understood that, okay, maybe from the beginning there was a wrong approach. We did start with the materials and in the classical way. Take a material, try to design. There is a specification for the nickel-based material with this chemical composition. But if you will use this chemical composition in this printer, you will get a glass, not a metal. So, and this was the first our, let's say, observation. We need to work with the materials. We need to make a work with the chemistry in order to tune the chemistry. And then, let's say, get the materials. Also, what I would like to share with you, from our point of view, is really very important. In order to, let's say, to be quick with the application, what needs to be done? Classical approach. You have a materials, you have a technology, like a manufacturing technology. Then what you are doing, you are taking design tools, you are trying to design with the limits of this technology, and then, let's say, do the manufacturing and then use the components. Here it's opposite. We need to start from another end. And this, I hope that it's helped us really to understand and be relatively quick and successful in the application of this technology. We start from the technology which is available. There is the technology at this time, and we are talking today about the SLM, selective laser melting. So at that time, this was the most developed technology. And we found, okay, this is the technology, this is the price for the powder, this is the price of the equipment, and this is hourly rate for this machine. One issue is to apply this technology for the development and for the prototyping when the cost is, of course, important, but maybe not so important compared to the serial production where you are selling the parts. So this means that cost is already defined. And then the next step is to define the application. If you will apply this technology for something simple, this component will be too expensive, they will be like a gold, and no one will buy from you. So, and this is how we came to the, let's say, application. We said, okay, we know hourly rate, we know the complexity, we approximately know what kind of components from the cost point of view, manufacturing cost point of view, could be applicable for this technology, this particular technology. And we came to our burners. It is one of the most successful gas turbine currently in the market, in the range of 47-50 megawatts, was designed and done in Finspång. We found we have some components which are available there and quite expensive, complicated, and it could be reasonable to use this technology in order to further improve the performance of these parts. And again, due to the fact that we are working with the service organization and we have a ownership in the area of the repair, we said, okay, we will start not from the manufacturing, we will start from the repair. And then how we pick up this burner, and the idea was to, let's say, to do the repair of the burner. Usually we have some kind of oxidation and cracking on the tip section. This is what you can see. It's here, usually. And we said, okay, but let's try to cut the damaged piece, put into the machine, and then print on the top, the new part. Yeah. So, and this is how we came to this component. So, and we also found that in order to be really reasonable in terms of the cost even of this repair, it's quite important to consider the redesign of the printer as well from the beginning. And this is what I would like also, this is one of my message from today could be the following. Guys, if we would like to be successful here, one company will never, let's say, cover all these topics in the chain I already explained. We need to cooperate. We need to cooperate with the universities. We need to cooperate with the suppliers of the equipment. We need to cooperate with the suppliers of the material and powder in order to let these guys know what we as users of this technology are looking for. So, and then after 1 year discussion with the years, so in the 2009 we bought the first machine. In 2012 we bought another machine which was specifically designed for our purpose, where it will be possible to put the burner inside of the machine and print on the top what we need to print. So, and this was done in the 2012, and you can see already in the 2013 we put the let's say developed qualified burner into the commercial operation. So actually it was a really very quick way, about 5 years, to let's say understand the problem, to define the materials, and to define the components which could be done. So, and we currently are in the fleet, and afterwards I will show you. This is also quite important point to share with you where we are in terms of the field experience, how reliable these components are. Can we run these components in the very high temperature level in the gas turbine or not? You will see this later as well. So, and at the same time, we were working with the new gas turbine, and our designers at this time already got, let's say, access to this technology. They found that it's not only good and perfect tool in terms of the speeding up of the development and prototyping. This could be a good tool to design something and to manufacture something which is not possible to do with another technology. And due to this high restriction in the emissions, in the temperature, dynamic behavior in the combustor, and then reliability, they came to the, and this is what you can see here, they came to the swirl, which is a part of the burner. So at that time it was found that it's excellent design, but we cannot manufacture this in the classical way. We need to use the additive, and this was the first time when we applied the additive manufacturing for the manufacturing stuff. Yeah. So, and yeah, so this was our first experience, and currently we're using this technology for 3 major purposes. First of all, rapid design and prototyping, and I will show you an example where we are capable to squeeze the design time from few years just to a few months. Then we're using this for the rapid manufacturing, and then we're using this for the rapid repair. And we are really pleased to share with you, so that in general 8 years, this is a quite long period, but looking on another technology, start from the scratch and then come to the serial production, it's from another hand quite quick step. So in the 8 years we were capable to go from the starting point, R&D project, to the serial production. And also on this picture you can see our workshop in Finspång. So we have a first step, and we found that this really very challenging and very, let's say, promising technology. We are after, let's say, 8 years of exercises, we decided to expand. So now we will go significantly forward with this technology in order to gain additional experience and then understand how we can, let's say, understand the design issue, because this is another point which was one of the major stoppers, is a mindset, our mindset, designers' mindset. So with the classical approach, just, let's say, print what is already there, you will never come to the, let's say, reasonable cost, and you cannot utilize all functionality and all opportunities from this technology. So this means that we need to change the design mindset. And then here we also face quite interesting issue. So usually in the company, what is the most important in the company? This is the experience of the people. This is the key experts, their knowledge and experience of the company. We found that in this particular case, you can, let's say, face a conflict. So the guys with a huge experience could not help. They could be the stopper of this technology because they already used, they know where to go. But with this technology, we need, let's say, to open. And this is why, again, there's a communication and the cooperation with the universities. Building of new engineers with another mindset is very important. And this is also what I would like to share and send as a message to you guys. So, and in order to really to step into the design issue and then understand better what could be done not only in the power generation industry, but in the space, in the, let's say, in the air industry. We, in 2016, we acquire a company called Material Solution in the UK. And by doing this, we get additional knowledge in the processes, in the materials, and in the design tools as well. Today, we are working together with these guys. So if I will briefly go through this one in terms of the benefits, what kind of value this technology help us to get. So we are talking a lot about digitalization, digital transformation. And we believe that additive manufacturing is a part of the digital transformation. This is what you really can touch. And then there we can see a three-dimensional, let's say, transformation. There's a transformation in the product, transformation in the manufacturing, and what is important also, transformation in the business approach. If in the past it was quite important in order to go down with the cost to have more standardization, that in this particular case we are coming to the more or less a customer approach. So we can customize any product and then track this product. So and the combination of this transformation in the design, transformation in the manufacturing and the business help us really to integrate the overall approach. And today, the guy who is doing the design, he's not just a designer. He gets a knowledge already from the manufacturing because these two pieces there are integrated. And this is the additional requirements to the staff. What kind of a competence, what kind of a knowledge these guys have. And we're coming to the conclusion that more and more integral knowledge and competence will be required in this area. I also would like to share with you some numbers which we came through what we already did. Maybe start with the first one. This is a reduction in the greenhouse and then emissions. Just due to the definition, so in the using of AM technology, we do use the amount of the materials which needed only, not more. Moreover, we can quite often reuse many times the powder, so this means that there will be positive impact into the greenhouse and then emission reduction. So there we found that in average, on the based on the components we have, we can at least reduce by emission by 30%. But in the case which I did show you, this burner repair, we did improve the emissions by 80%. So this means that just to do this repair, we need only 20% from the power we will need to use the normal classical repair process. In terms of the resources, this is also quite an important message. So again, due to definition, due to nature of the additive, we can use less materials. What is your opinion? What is your expectation? How much we can, let's say, save there in terms of the materials? 20%, 50%? Any? 65. Great. So in terms of the reduction of the development time, so there, as already said, we can come from like 2 years to just a few months, and then we found that based on what we already did is about 75%. And then flexibility in the design. Also would like to challenge you in terms of the percentage-wise. Any advice? Any? Yeah, almost 100%. Yeah, you're right. So and so faster repair. So there we did found also that we can do this 10 times quicker. So and of course we would like finally to have a significant speed up of the overall delivery process. Yeah, and this we are looking for the delivery time reduction by 50%. So I also would like to share with you some kind of examples which we consider as a breakthrough example, and this is the first time when the blade and I took it in my hands when the blade was designed, when the blade was put it into the. It was designed, manufactured with the additive manufacturing and put into the engine for the validation. So what also I would like to say that there will be no wrong message from here. Today we can do design, print and validation in the engine, but we cannot, let's say, keep this blade for 4 or 5 years continuous operation for 30,000 hours because we are still working with the nickel-based materials for the rotating parts. It's not completed yet. But what we did in the 2 months instead of 2 years. We came with a few versions of the cooling system of the blade. We performed so-called rainbow test. We put into a real engine these blades. We perform the test. We pick up the best cooling system, and now we can do the printing, casting of the blade in the normal way. But we save 2 years, and we did consider 3 different versions of the system. So we pick up the best one, but in classical way, in 2 years you can pick up only one variant. And what is the, let's say, consequence of this approach? Usually designers are very conservative. They, let's say, afraid to make a mistake. This means that with this technology, we really can take into the life something is extremely, let's say, challenging, but at the same time extremely effective. So what I would like to share with you, to show you a video, so that there is like a saying, it's better to see once rather than hear 7 times. So please take a look, because this is really the story about this blade. Could you please show a video?
The additive manufacturing process enables us to manufacture parts that we cannot manufacture today with normal, traditional manufacturing processes. That enables us to be more ingenious in terms of how we design our turbine blades, how we cool them and how we life them.
Turbine blades has always been, I feel like, a vision. It's a real target. It's the most challenging area of the turbine. So if you can print a turbine blade, you can pretty much print anything. And we've proven over the last couple of weeks now that we have been able to print a turbine blade and test it in an industrial gas turbine engine.
In Lincoln, we're testing a 3D printed blade, and we believe this is special because it's the first time anywhere in the world this has been tested at full load conditions in a gas turbine. We test these blades very quickly. In 1 hour, we run the engine at full load. We put a probe in here to measure the material temperatures, which tell us how long these blades will last in a turbine.
Now, the turbine blade itself is this particular blade. Now, this is the high pressure turbine blade of a 13 megawatt SGT 400. Typically, we have to do all of the design, analysis, the aerodynamics, the work in terms of heat transfer on this blade 2 years before we can actually then understand in an engine how it's actually going to perform. What additive manufacture does, and this is the additive manufacture blade that we've actually tested in this engine, this gives us the ability to cut that lead time down from 2 years down to 2 months.
It allows us to create new designs, to get more efficient engines, more efficient designs into our turbines, tested, and then onto ultimately our customers.
We will see quicker development times.
You don't need this very expensive tooling in order to make your products. So that makes additive manufacturing perfect for design modifications. You'll get there much quicker.
The basic process starts with receiving the model from the customer. We'll then take that model and slice it into very thin layers and export it to the machine. The machine then builds it up in a very thin layers, 20 microns, using a laser to melt all of the metal powder together to create the final product. Although we've been developing the technology for 10 years, we're still very much at the beginning of the journey of what this technology is capable of. To a certain extent, if you can design it, we can make it.
None of this would have happened without the tremendously close collaboration between a large number of Siemens units. It really is ingenuity for life to enable us to satisfy all of our customer needs.
Yeah, and then with this video, I also would like to, let's say, to demonstrate how kind of a, let's say, mindset transformation can take place. The guy who is the head of engineering, who, let's say, promote this blade, 2 years ago, he said, no blades in the engine, only after my dead body. Yeah? Now, you can see he's pushing this technology across the organization. So I was very proud that this kind of a blade and our team was awarded, first of all, in Siemens. We have a yearly awards, and maybe most important is even that our let's say results were recognized and awarded by ASME conference as well. So we got last year the ASME award. So another type of the application So another type of another application is like a production where we can significantly reduce the number of the components, and then instead of a complicated have only one, by at the same time increase the lifetime, improve the efficiency. So I also would like to share with you our experience we currently have. From my point of view, this is one of the most important. So how many hours we did accumulate in the very tough environment condition for the burner? More than 30,000 hours for the repairs, for the swirlers, more than 30,000 hours. We already put into the commercial operation the burners, and there we have a quite good also cooperation, co-creation with our customer. Customer is willing to give their engine for the prototyping, for the validation of the components if we are doing this in the right way. Maybe challenges, I will skip it. I would like, this is what I already mentioned. We recognize that the cooperation is extremely important. And here you can see that we recognize this part, and we are very active. Siemens is very active in Sweden in terms of the cooperation with the different universities, research centers. And maybe finally our vision. So we would like, first of all, to utilize the latest design knowledge and then technology, and utilize the X-ray tomography for the getting quick access to the geometry. We would like to have a fully automated workshop we already have in Finspång, and in the future we are looking for so-called printer clouds, so that our printers will be distributed all around the world in the Siemens workshop, very close to our customer, and we will come to the principal spare parts on demand, so that we will use the digital twin of the old components, which will be used for tracking of the components, and then print the components only when it's needed and in the area where it's needed. So this would be my last slide. Sorry if I put a little bit squeeze but maybe during the plenary discussion we can discuss the challenges and opportunities of this technology.
And I'm sorry for rushing you. So
okay. The only question I let's say give you guys a blade. It would be great if I can get it afterwards back. And then it's another
I think that's fair
for the air derivatives.
Okay. All right. Now it's time for the next point of our program, where Edvin is coming back on stage, and he will present this little brochure, which I'm very proud of, because I personally took a great part in actually designing this. So the floor is yours.
Yeah, thank you very much, Adam. And I think I would like to extend a big thanks to both Adam and Sofia, who sits behind Adam, who has been assisting in putting this together and interviewing the companies and the institutions in terms of getting a picture of, I mean, what do we need to focus at? And we also want to recognize the work that was put down by the Sverige group in Sweden last year to make a sort of a state of the market, which we have based our analysis upon. I mean, but what we needed to do when we got together in our industry group was really doing a sanity check and seeing, are we aligned in terms of which areas do we believe that we need to focus in. And what we've also done in this process is expanding that circle and inviting other industries and also academia to have an opinion on it and add to sort of these questions. And going into that, we have highlighted, I would say, 3 areas, which is like the core areas for our industrial group. And I mean, one is really know-how, and I think that is something that has been said many times today, but that is actually understanding these processes and understanding how to use these processes, which we believe is by integrating the elements of additive manufacturing into the educational system, but also having an action plan for how to handle the big amount of engineers that are actually out working today, which needs to have a possibility to approach these technologies. Secondly, I mean, looking at materials specifically and the manufacturing process, in Sweden we have a big tradition of big know-how when it comes to materials development and understanding materials. We have companies like Höganäs, like Sandvik, who are really, and Uddeholms, who are really active in this field. And we see that the materials that are available today, I mean, it usually comes from an angle where, I mean, they were originally tailor-made for another manufacturing process. So capturing that and seeing how we can sort of use the public funded system to leverage that know-how. And what's also been discussed today, I believe, is the end-to-end thinking. I mean, that the additive process is not a standalone process. So we also need to capture the aspects of post-processing as well, which we also have a good tradition of in Sweden, I mean, through companies like Sandvik, for example. And then the third one, I mean, bringing in these powder materials containing high levels of nickel, chrome, cobalt, it also raises the question, I mean, are we having the right devices in place in terms of understanding the effects it has on us humans? And we believe that that is something we will need to answer in the coming years. And because, I mean, we don't want to risk setting up these big production areas and then breaking the development because we see a potential EHS issue. And there is not enough done in the research field today. So we're really hoping that this can be an area where we focus. And the agenda is printed. It's on various places in this facility, and also on the upper floor we will have the lunch. So if you haven't read it, grab a copy. Feel free to distribute it. Feel free to get into the debate and contributing as well. I mean, this is made out of where we are today, but it's also going to be a continuous process on how we bring this forward. And I think that's about it, what I wanted to say about the strategic research agenda.
Well, thank you very much, Edvin. And as Edvin said, there are several copies upstairs. There are also more copies that can be requested from Edvin. And I'm sure that if any one of you in this room would like to have a couple of copies, please don't hesitate to email Edvin.
Yeah. Take care of that.
Excellent. Thank you very much. We will now move over to the concluding session of this morning with a panel, and the panel will consist of Vladimir. Please come back on stage. Now we can ask all the questions we want to you. In the panel, we will also have the pleasure of having Hans Enoksson. Please welcome on stage, and Erik Ronne, who I saw somewhere in the room before. There you are. I have your name tag. You're welcome. And we all know Vladimir from before. Hans Enoksson, you maybe not everyone in the room knows you. You used to be the president of GE here in Sweden, and you're now running a different kind of company.
Well, yeah,
please.
I was responsible for GE for 10 years, retired last year, actively involved in not so much advanced manufacturing. We acquired Arcam at the time, but also in the digital challenge in general. I worked a lot with that. And as you mentioned now, I'm chairman of a small company that delivers technology to NASA, but also moves this to industrial space, called Unibap. Putting, you can say, intelligence and eyes on robots is one aspect. Working with a couple of participants here in this group. Very interesting future, I would say.
Yeah. And Erik Ronne, you are Vice President of Innovation at RISE, so you're a colleague of mine.
Yeah, that's right. I also have a chemical background, been 20 years in AkzoNobel as Innovation Director. And AkzoNobel does also investigate the possibilities to make binders and powders for AM. So I don't have any background actually in AM specifically, more into innovation generally.
Excellent, great. And as I said in the beginning, I hope that this will be interactive, so please don't hesitate to raise your arm if you want to ask a question to any of these guys. You have microphones, all of you, next to your seats. one of the challenges that Vladimir mentioned and that many of the other people here have mentioned is the challenge of collaboration, that no single company can do everything by themselves. Vladimir, you didn't get much time to develop on that collaboration slide of yours. Maybe this could be the time. What would you actually want from the ecosystem?
Yeah, as I already said, this is a technology where collaboration is really very important. It's a time-consuming, everything is new there, and it's difficult. Even, like I already said, GE and Siemens company, which have more or less all competencies needed, it's difficult really to put everything together. So this is why cooperation with the different communities is important. So powder, as already said. So it also was mentioned during, let's say, our discussion that, I believe it was you, Edwin, who said that the powder was tailor-made for the certain technology. Now perhaps we need to reconsider. Maybe we need to find another way how we should work with the chemistry of the powder. With the chemistry of the material and then make a powder. What kind of rejuvenation we can do for the powder in order to, let's say, reuse this many times and then even improve maybe the properties of the powder. It cannot be done within one company. So this is why we need to cooperate. But at the same time, I strongly believe that this kind of cooperation could create or should create some kind of a competition. Why we have a very expensive powder, up to 10 times maybe more expensive than the raw material? Because we have a just limited number of the powder providers today. Let's do the cooperation. Let's raise the competition, and you will find that a lot of smart ideas, a lot of smart proposal will come. And then talking about the software development. So, okay, we have a quite powerful department in Siemens organization who is working with the NX, who is working with the expansion of this stuff, but we cannot handle everything as well. Now, with all these digital tools, we need to come more to the validation, more to the simulation. So, and with the simulation, it's quicker and cheaper to do first simulation of the process parameters. And today, with the, let's say, this computing power and knowledge, we can do this. So let's do simulation first and then print. So this will help us also to simulate the distortion, to residual stresses, process parameters, to even to include this into the closed control loop so that we will do the monitoring of the process parameters and then even be capable to improve the quality of the product. So, and the same with the universities. So it's a lot of smart guys sitting there. And then innovation. Innovation is not necessarily invention of the wheel. Innovation is to understand what it's already developed could be used from one industry to another industry. And I believe that university, this is a way where we can get this kind of support. And manufacturing, it's...
But Vladimir, in all honesty, I mean, if someone comes to you or to Siemens in Finspång and say, "I've got this fantastic idea about how to with a piece of software or a piece of process engineering or a piece of quality control or whatever have you," would you listen to them or would you let them in, give them half an hour?
Absolutely, because what I already said again. So this currently the young guys who are thinking outside the box can contribute more than the guys who already have a 40 years experience. So yes, of course, we will be listening and we will find some kind of a cooperation.
Okay, that's a promise to everyone out there. Okay, you're welcome to Siemens. Hans, switching over to you for a second. The company you're currently working in have a lot of interesting ideas about quality. Perhaps you could explain a little bit how that technology could be used as a qualifying element within the AM arena.
Yeah, one aspect is, of course, continuous quality control, right? And what we're working on is working from a CAD drawing and then continuously monitoring so that the manufacturing process follows that, and as soon as it sees a deviation today, it can then stop that process. That's one way. It's an early stage. I mean, what we're all talking about is technologies that are in reasonably early stage, but in the process of maturing. I also would like to add to what Vladimir has been talking about. I think the challenges that we're going through is where can we apply what technology and the responsibility that suppliers have. I mean, the reason why GE acquired Arcam was that we had invested so much on the production side, on the quality side, so that we felt that first of all, we need a lot of machines ourselves, but then also to provide standardized technology to customers. We discussed briefly. We do need to come to a maturity rate where these a lot of responsibility can be assumed by the suppliers of equipment, and systems thinking, looking at what powders can you use for what. So we have, I've followed many technologies. I worked in healthcare a lot, followed CT from very early stage and MR and so on. And today, what they were 20, 30 years ago it's such a huge difference. And if we look upon this 20 years from now, we will see this will be standard. And what GE is working on is actively to get production speed up significantly so we can use it for general manufacturing. But also looking at design concepts, inviting people, as you say, the young people. We do challenges where we invite people for provided solutions. The first one we did was 7, 8 years ago, I think. It was how to put engines on wings. And one of the persons actually that qualified was a consultant to Koenigsegg, who provided a solution which was 85% lighter and very efficient. So how do we tap the global brain?
But that is, I mean, as you said, tapping the global brain, that is definitely a challenge, because there are so many industries right now screaming for competence. This is certainly one of them, but you're definitely not the only one. So maybe I should ask this question to all of you panelists. What is it within AM that would actually attract young engineers to go into this subject? Or I mean, sometimes you can find business opportunities, sometimes you can find engineering challenges, sometimes you can find just great companies to work for. What is the appeal of AM to young engineers?
It's a growing business.
You're seeing it from a business point of view, okay?
I should know the statistics better, but we did a study on this, and we found that the biggest part was the challenge.
Okay.
Young people like to provide a solution, and that was the biggest motivator. The second one was to say enhance technology, but the third one was financial motivation, really, how to earn money from it, which was sorry, I need some water, I think, was interesting actually to see. Can you open? Okay.
I think you can add the opportunity for creativity also, because it's such a new industry. A lot of opportunities not seen yet, and I think that might be really interesting for young students and other.
Yeah.
And I would like to be short
please,
with this message. So here actually the young guys can put their dreams into the reality in a very quick way. So they can see immediately the effect of what they're thinking about. And we talk about one of the benefits of these technologies, just talking about the gas turbine application for this stuff. To increase efficiency by 1% point, you need to increase the firing temperature by 100 degrees. In order to increase the firing temperature by 100 degrees, you need to develop new materials. With this technology, you can keep the same temperature, but you can improve the efficiency of the turbine because you will use the more effective cooling system, which are not possible to do with the classical. And the young guys, if you came into the office, into the business, and then simply in the 2 months come out with the blades, which is like a 3 times longer lifetime than the conventional design. Is this the effect? Of course, this is the effect. It's a immediate recognition, and this is the immediate release of his idea in the reality. I believe that this is one of the, let's say, driver why the guys really stepping, and this is really very. And this is what we can see, by the way, currently in Siemens organization, so that this innovation team is really getting very popular. And then, at least in my service organization, where we have a quite big TI community, if in the past the well-developed guys moved from the service to the new unit because it was, let's say, respected higher, I can see right now opposite wave. The guys from the design are coming to us, to the service.
Okay. Interesting. But that's a good point. I mean, that is a very good sign. So Eric, I mean, we talked about a lot about collaboration before, and being from the institute sector, from the research institutes, it's hard to get around the question: what should the institutes be doing? What should we, as a research institute, be doing?
I think first of all we should provide a kind of innovation infrastructure for this technology. There have been a lot of presentations from large companies here, but I think we can really support SMEs also interested in this technology and who have not the possibilities to invest in competence and instruments. Just to make both design competence and equipment available publicly.
Yeah. But is this really
an important role to take?
Yeah, but is this really an SME business? I mean, we're seeing we're seeing most presentations here have told us about how many years we worked on this and how many millions of whatever currency we invested in this, and how could an SME contribute, or how could an SME do business?
Well, I think, looking at the importance of the SMEs for the big companies, because the small and medium-sized enterprises, they're an integrated part of their supply chain. I mean, not all of the big companies manufacture their own parts. And I believe there's really, in this journey for the big companies, the SMEs also needs to be sort of incorporated on that journey to ensure that when it's actually time to move into production, I mean, they are there as well in terms of competence. And I mean, they also need to understand the possibilities with this. And if you collaborate with a big enterprise, then there's definitely room enough to make the investments and get sort of the production capacity yourself. But I think the right way is to bring them on the journey, not come when you have done everything and say, hey, by the way, can you produce this part for me in 5,000?
So constant collaboration over longer periods of time is would be an appropriate way to go forward.
I believe so.
Yeah. Okay, so we are here today. We have a lot of Swedish companies who have begun their AM journey, large and small. We all appreciate that this is a technology, and more than a technology, it's an engineering mindset that will make a lot of shifts in the industry for the next decade at least, to maybe more than that. And we have the SRA, the Strategic Research Agenda. So how do we go from here? What would be the next step? I mean, we have all agreed that we have to work more closely together. We have to involve more people, young and old, and experienced and not so experienced. So what would be, in your view, the next natural step? Let's start with Vladimir.
Yeah, just to continue what we already studied a few years ago, I did show you the Swedish map.
Yes.
And all these dots, this is, let's say, the point of our cooperation. We have a quite good cooperation in the most critical areas, as already mentioned. This is a powder. So, and then different technologies as well. With the powder, we start to work with the Sandvik. Right now, we're working with the Höganäs. In terms with the Höganäs, we're also working with the there's another technology so-called binder jetting technology. So Edwin did show the different technology, and this is quite important to understand that all of this technology have a certain application and have a certain benefits. So, and we found that with the binder jetting, we can really come out significantly for the cost reduction, but for the certain components, not all of them. And this is the beauty. So it's just to continue what we did, and then we would like to have a, let's say, more link and more cooperation, so that it will be not like islands. These islands should be bridged. So, and it would be good if we really find a way how we can bridge this.
So if you can wish one thing, if you can make one wish to the ecosystem, it's build more bridges. Is that, do I understand that?
Yes,
correctly?
correct. Because again, looking on the Sweden, we have everything what we need here in order to have, let's say, independent ecosystem.
Okay. So Eric, what would be your next natural step?
First, from an internal perspective, in RISE we have at least 3 daughter institutes with high AM competence, and we have 3D printers spread out all over the group. So one first step would be to focus a little bit and build up capabilities, not necessarily in all in the entire field, but perhaps focusing on certain areas of AM. Then I see also, when I hear the discussion here about binders and powders, etc., it's a little bit a Wild West now. It's a very new technology and not very much standardized yet, not too many general solutions. And I feel as a technical institute, we for instance, we govern the Swedish kilogram and the Swedish meter and the Swedish time and all SI units. And certification and standardization is a kind of bread and butter for us. And I feel we could build up something good around standardization for AM and contribute with good analytical techniques, non-destructive techniques to analyze from the very first design step to the post-manufacturing processing.
And maybe just a little bit add to this one. So why we still have an issue with the standard and regulation in the overall? Yeah? Because it's not a simple task. No. So we found that everything there is integrated, but again, looking back to the, let's say, to Sweden, to the place where we are currently, we have a really limited number of, let's say, participants, or not limited, but well-represented number of the participants. With the right focus, maybe we can come with our, let's say, standard and regulation first, much quicker than across the whole world. Yeah.
I think that our friends from NASA can also testify that writing these standards is not an easy task.
Yeah, that's true. But I would want to encourage or emphasize the importance of the open standardization in terms of that's the key to, especially relative to SMEs, getting them involved and enabling them to work. Getting the open standardization in place is key, and I think in terms of mentioning where do you want to start with that, there's been a lot of debate in our country about what are the roles of government entities in terms of providing independent data, and what are an ongoing and continuous debate about how can the corporate world make decisions on what the terminology we use is pre-competitive. What are technologies, what are pieces of information, key enabling pieces of information that companies are willing to say, okay, these are fundamental and not something core to my competitiveness, and therefore I'm willing to cooperate openly with the larger industry, government entities, academic industries, or academic entities, and provide that foundation that Vladimir's talking about in terms of things that are too large for any one entity to encompass. And I think that's identifying those and getting an agreement to say, okay, here are key enabling technologies that the industry can consider as pre-competitive, and establishing that as active areas for standardization is the early key to keeping the industry moving and keeping it accelerating it at the rate that it currently is.
Super, thank you. More comments, questions, please?
I thought of adding three things.
Please.
Standardization, of course, I think is important for any industry to evolve, right? Secondly, I would like to challenge when we say that Sweden is not good in this area. I think in certain aspects we are very good. We have, Arcam was a small company. We have a number of small companies working in this field with very good technology that actually we are able to provide to you to a limited extent to the US due to the ability of making business with the US. But then thirdly, I would say, as always, and the initiative now ongoing, that we gather industry around challenges and make small and large companies cooperate so that we do evolve. Because I think, again, we have Höganäs, we have small companies and so on. We can do a lot here, but we need to work much more together.
I think that's a very important message, that we might be small, but we're not as bad as we sometimes think we are. We are much better than that, and we can do a lot of things. Yes, please.
Well, hi, Thank you for a very interesting seminar today. My name is Elisabeth Sagström from Sverige IVF, soon to be RISE.
Welcome.
Thank you.
Welcome.
Just want to raise to you that there are available test beds for AM in Sweden, and CIMA, you know, not a lot of them, and also the colleagues at KIMAB here in town. So for small and medium-sized companies and also larger companies, there are open test beds for additive manufacturing, and we would like to welcome all interested parties to them.
Very good point. Thank you.
Thank you. Yes, please. Please use the microphone. Thank you.
Yes, my name is Sima Valizade, and I am working at Swedish Association Engineer Industries, which means Teknikföretagen. And I am a director for 12 test beds for Sweden within production 2030. And we have 2 test beds, which is just focusing on additive manufacturing out of those 12. And one of them is working very unique just to create and work through the supply chain from manufacturing until supply chain process during the productification of any prototype or maybe any tools. Then you are very welcome, as Elizabeth said, to just join us and just try to contact me, or I can just inform you where you can go and try to find out what you want to develop and how you want to work. And the other one is just focusing on large scale manufacturing. It means it's not limited to the size. Please just contact us and then we will help you for collaboration. Thank you.
Thank you. Okay, there's one more comment down there. Please use the microphone.
Hi, my name is Fredrik Lawell. I'm from KTH in Stockholm, and I'm running a 3D program on glass. And I'm interested in if you see needs for other materials like glass, semiconductors, or even living samples like biological 3D printing. If you have any knowledge or interest in such things.
I'll leave the question to the panel. Who wants to take that?
Yeah, I think all materials that can be printed are of interest. And in RISE, for instance, we 3D print food, entire dinners. And we also have a 3D printer for wood up in Umeå. So we should not restrict this discussion only to metals. Yeah.
That's 2.5D.
But maybe the food may be like a decoration, very nice.
Okay. I think that in the interest of time, the last question goes to Edwin. What would be your next step? What will you do tomorrow?
Go home. No, but really the next big steps for us, I mean, now we've sort of consolidated our thoughts within the group of how we want to move things forward. And what we will do is try to actively engage our owner group in different research projects and so on, where we know that there is a need. I mean, we're in a position where we can see similarities, common areas, and sort of try and leverage that into new programs and new projects, apart from what we're doing sort of on a day-to-day business with these companies.
Super. So with that, I'd like to thank the panelists. I'd like to thank the audience. I'd like to thank Amexi and Eva for hosting this event. And now I believe lunch is served upstairs.
Yeah.
Is that so?
Great.
Okay. Yes. So just before, let's give the panel a hand. Yeah. Thank you.
So I'll be very short. I got the job to try to summarize this presentation today. I mean, we have moved from outer space, we've passed by Mars and the moon and come all the way down to powders and nanoscale. So how do you summarize it? And I'm sure you all have your own summaries, but the main points that I've picked out today, and we've had a very strong case presented by several of the speakers today about the case for additive manufacturing, that it is disruptive, it will probably radically change the manufacturing industry and how we look at how to make products, and not only in metal, all different materials. But as NASA, our speakers from NASA have made very clear, additive manufacturing might make complexity easy. We can introduce complexity, but it's not for free. And the challenges that we need to overcome and what we need to understand in terms of the processes must be understood all the way from a powder to a qualified product. We also need standards for that, as my number 2 big observation. And the third one, which was summarized in the debate here afterwards, the way to go forward is collaboration. And saying collaboration is really easy, but how do we create the incentives to actually do it? And talking to our colleagues from NASA last night, we were discussing some of the challenges, and it was mentioned that most likely many of the big industries or companies that we are talking to here or listening to, they have solutions, but they've spent many hundreds of or many man years and many millions in developing them. How can we compel them to share that? They could be the final pieces of the puzzle to actually move this forward. So MEXI is obviously one such attempt, try to get industries to work together, but we need to do it on a national scale, and we also need to work outside the boundaries. That's my summary from today. I hope you will have a similar one. Please talk to all the speakers here up in the lunch. Thank you very much for your participation.